We will now begin section 3.4 and talk about variation and multivariable functions. We begin with an understanding that a number of natural phenomena exhibit the mathematical property of variation. What this means is that one quantity varies or changes as a result of a change in another quantity. Our definition for direct variation, which is one way that we can look at variation, says that y varies directly as the nth power of x, or sometimes we say that y is proportional to the nth power of x. If there is a non-zero constant k, we call this the constant of proportionality, such that y is equal to k times x to the nth power. The easiest way to understand this formula and this concept is to look at an example. Hooke's law says that the force exerted by the spring in a spring scale varies directly with the distance that the spring is stretched. If a 5-pound mass suspended on a spring scale stretches the spring 2 inches, how far will a 13-pound mass stretch it? We will follow a series of steps to solve a direct variation problem. First, we will write an equation that expresses the nature of the relationship. So we know that the force varies directly with the distance. So if I look back, I'm going to take a similar stance to this. We're going to have force on one side. We're going to have k, because k is our constant of proportionality. And then we're going to have x on the other side, where x represents the distance that the spring is stretched. So we're going to write an equation that looks like F is equal to k times x. And this is what I gather from the first sentence. This says that the force, which we are using an F for, varies directly, which means that we have a constant of proportionality that relates them, with the distance. And distance is going to be the x. Once we've written the equation to express the nature of the relationship, the second step is to use the given information to solve for k. So as I move to the second sentence, I know that a 5-pound mass suspended on the spring scale stretches the spring a distance of 2 inches. All right, now I'm going to flip over here just so you can see this picture. Here's your spring scale. You have your pounds, your 5-pound mass suspended on the scale, and you can see that it has stretched the spring down 2 inches. So what we're going to do is plug in that information into our general equation. So the force is the mass that is being suspended on the scale. So we're going to put a 5 in for the F. Remember that we're solving for the k. And x is the distance that the spring stretches. So x would be 2 inches. When we solve for k, we're going to divide both sides of this expression by 2. And so k is equal to 5/2. So again, first step is to write an equation that expresses the relationship. Second step is to use that equation with the information that you're given to solve for k. And then the third step is to take your formula and update your formula now with the k value. We know that k is 5/2. and try to answer the question. The question says, how far will a 13-pound mass stretch it? So if we change the 5, the force, to 13, we want to know how far will the spring stretch. We want to know the distance. And so we're going to solve for x. Now, when we solve for x, we can either divide both sides by 5/2, or we can multiply both sides by the reciprocal. So if we multiply here, the 2's will cancel, the 5's will cancel. On the right, leaving me just an x. And multiplying over here, we get 13 times 2 is 26 over 5. And so the spring stretches 26 over 5, which is 5.2 as a decimal inches, if you hang a 13-pound mass on the scale. We'll now look at the concept of inverse variation. We say that y varies inversely as the nth power of x, or that y is inversely proportional to the nth power of x if there is a non-zero constant k such that y is equal to k divided by x to the nth power. The method of solving an inverse variation problem is identical to that we did in the first example. Here's our example for inverse variation. The weight of a person relative to the earth is inversely proportional. So right now I know if it's inversely proportional, that this formula should hold. So I know that I should be able to set something up, and we may need to change the letters, but y is equal to k divided by x to the nth power. So the weight of a person is inversely proportional to the square of the person's distance from the center of the earth. Okay, let's go ahead and do step 1. Step 1 is to take this concept and write it expressing the relationship between weight and distance. All right, so let's use a W for weight. So I'm going to say W is equal to, instead of Y is equal to, we'll have K on the top of our fraction. Remember, that's going to be a constant that we're going to find in just a second. And then X to the N. X to the N will be the distance. And it says to the square of the person's distance. So I'm going to make it X to the second power. So our formula is W is equal to K over X squared. Now recall that the second step is to take the information that you're given and use it to solve for K. So what do we know? Using a radius for the Earth of 6,370 kilometers, how much does a 180-pound man weigh when flying in a jet 9 kilometers above the Earth's surface? So we're going to take this 6,370, which is the distance from the Earth. So that's going to go in for the X. We're going to leave the K on the top. So K divided by 6,370 squared. And then we're going to need to find the weight. So we know that the person weighs 180 pounds. So I'm going to put 180 in for the W. All right, so we have a radius of 6,370, which represents our distance. That's our X. And we have the man's weight, which is going in for the W. And we're going to use that in order to solve for the K. So the easiest approach here to solve this expression is probably to cross multiply. So remembering that the 180 is technically over 1, we would have 1 times K. And then we would have 180 times 6370 squared. And that's going to be a very large number. If you multiply it out on your calculator, you are more than likely going to get an answer in scientific notation. And so I'm going to go ahead and write that down. 7.3 times 10 to the 9th is what I would get when I do that multiplication. So a number where the decimal is moved 9 places over to the right would be our answer. All right, so now we use our formula and we update our formula. So I'm going to take my original formula, W is equal to K over X squared, and I'm going to plug in my K. So I am going to erase the K, and in its place, I am going to put in 7.3 times 10 to the 9th. Now, the question that we are being asked to find is how much does this man weigh if he's flying in a jet 9 kilometers above the Earth's surface? So we're going to be looking for the W. We need to know how much does he weigh. And he'll weigh something different than what he weighs on the Earth because he is flying in a jet 9 kilometers above the Earth's surface, and you have the gravity acting upon his mass. So we are going to look for the W, which means we need to know what to plug in for the X. So what is his distance? If the radius from the Earth is 6,370 and his jet is 9 kilometers above the Earth's surface, then his distance is 6,379, adding those two distances together. And so let's plug that in. So we have W is equal to 7.3 times 10 to the 9th. And we're going to put in 6379 squared for the distance. And we'll calculate using our calculator, and we can find his weight to be 179.49 pounds.